Guys, in the last video, we talked about the functional group of amine and enamine, and we talked about the differences and how they formed and what kind of reactions go forward in order to use them or in order to make them. All right, so what I want to do with this video is I want to basically start with this mechanism. I don't really need you to know the mechanism of the formations of these, but I think it is important for us to at least walk through and talk about them at least once, so that way you can walk away and say, yeah, he showed me that. We really didn't study it or memorize it, but you shouldn't be memorizing anything inorganic anyway. But we at least kind of looked at the mechanism on how these things were formed. So here is the first step of the mechanism for the formation of the amine. And what you're seeing is the traditional type 2 reaction mechanism scheme. This is a nucleophile. The nucleophile attacks the carbonyl carbon, and that breaks the double bond, and it shoves the electrons up to the oxygen. And that's what we're seeing here in this step. So the addition of the nucleophile has went on, but look at this. It's actually the nitrogen and the two hydrogens and the R group. So it's the whole thing at this point. So we oversimplified it in our reactions when we were talking about them, but the mechanism holds a little bit of different detail on the inside of it. The devil is in the details. All right, so this nitrogen containing group brings everything with it. When this double bond breaks, the oxygen is negative, just like it always has been negative, and there's probably a proton source that it can rip off, and that satisfies the oxygen to form an alcohol, just like it always has at this point. All right, so now what we have is an alcohol on the carbon, and we also have this positively charged protonated amine as well. So the reason that this is positive is because nitrogen at this point has more than 3 bonds. It has 4, 2 hydrogens, an R, and 1 to the carbon. So the base that got generated here is actually going to swing around and say, oh, look, that oxygen just ripped me of my hydrogen and I wanted one of them. But here's one for sale, and I think I'll purchase that off of Craigslist. So the base comes in and it says, hey, I think I'll take you, and bink, off it goes, and we generate the HB yet again. So now we have this carbon containing group that has the double bond destroyed, forming an alcohol, and also the nitrogen that is no longer protonated anymore. It is a nitrogen with a hydrogen and an R group, 3 bonds, and a set of electrons. And this is what we call a carbinolamine, all right, or carbinolamine, whatever, tomato. And this thing is not going to be very stable. It's not very stable because we have some resonance that can go on. We have some reactions that can go on in between the two different functional groups. And this is where the mechanism gets a little dirty. So the nitrogen can actually take its set of electrons and shove them in to create this double bond, and that forces the OH group to leave in form of water because another acid can come around and protonate the alcohol group to make a protonated alcohol. And we learned in the beginning of the semester that protonated alcohol is a very good leaving group. So we have the formation of the carbon double bond in, and we have the leaving group in form of a protonated alcohol leaving, and that begins to form our double bond in that we know is an amine. In this step, it is still protonated though, so we still need that base, and that base is going to come from up here yet again, because it was ripped of a hydrogen that frees up a base. The base is going to come back around and say, ooh, another one, I'll take it too. And away it goes. And this gives us our amine, which is a neutral nitrogen with 3 bonds. 2 of them are going to the carbon. 1 of them is going to the R group, which is a carbon-containing piece, and a free set of electrons. Now, am I ever going to ask you about this mechanism? And the answer is probably not. I'm not going to do that. It's just one of those things that I don't need to do, because we can simplify this process a little bit and predict these products without a problem. And I never really need to know this. The type 2 reaction mechanism, that is the most important. That's what I want you to focus on. That's what every one of these reactions are based off of. So the amine formation needs a couple of extra steps in order for this to work. Now, the enamine formation is very similar. The enamine is a secondary amine, not a primary amine. So you're going to see very similar steps here that are involved. So if I take a look at the first step, we see the traditional type 2 reaction mechanism. Nitrogen attacks the carbon of the carbonyl, double bond breaks, electrons get shoved up to the oxygen, forming a negative O. And now we have a nitrogen on the carbon that is positive, and because it's bringing the entire slew of groupies to the party. So we have a HB, some type of acid that can donate a proton, and that protonates the O-, forming an alcohol in this step. And this B that bing gets popped off will come back around and say, oh, look, a hydrogen. I'll take that. Thank you. And then that gives the electrons back to the nitrogen. So what we have is very similar steps in the enamine or the amine formation as in the enamine formation. So here we have a OH that is now protonated, or that has been protonated to form OH. And we have this neutral containing nitrogen at this point. Once again, we have this intermediate. It's the same intermediate as before. Well, we still have this acid that's present that still can protonate the OH group. And that protonated OH group, boink, is a very good leaving group. Again, we learned that in alcohol reactions. And the nitrogen with the two R groups here and a free pair of electrons. The free pair of electrons, this carbon needs them because the OH is getting ready to leave as a leaving group, and it needs something to take the place of that bond that it's getting ready to lose. So nitrogen takes these electrons and it shoves them inward to create this double bond in with the two R's that are hanging off of it at this point. This nitrogen, when that happens, says, I can't stay like this for long. I'm positive. I need to be neutral. I'm sorry. You got to do something. And that is where carbon decides to say, okay, fine. What I'll do is that I'll get rid of the hydrogen in an elimination, and these electrons will be shoved in to create a double bond, and then I'll give you these electrons back so that way you can be neutral again, nitrogen. So thank you for participating, and thank you for helping me out a little bit, but here is the payback from the loan that I took out on you. So here we have the formation of the enamine product. All right, so those are just the mechanism examples. That's really all that they are. And again, I'm not really going to stress on these too much, but overall, this is the concept that's happening to form those products. All right, now I want to do some example problems. All right, I want to do some actual example problems with these amines and our top 2 aldehyde and ketone reagents. So example number 1, let's take a look at this ring. Yeah, I'm bringing another ring back, but I'm making it a benzene ring. So here we have a delocalized network of alternating single double bonds, which is one of the requirements of the aromatic. Do you remember the multiple requirements for an aromatic molecule? I hope so, because guess what, folks? It's going to show up on a final exam. So here we have a benzene ring, and then off of this is a C double bond OH. So this is benzaldehyde yet again. So we're going to take benzaldehyde and we're going to react it with CH3, CH2, and NH2. Well, this was called ethylamine. That was one of those things that we talked about in chemistry 251, which was the nomenclature of amine compounds. So here we have benzaldehyde. We are reacting it with ethylamine. Now keep in mind, ethylamine is a primary amine. It's a nitrogen with 2 hydrogens and an alkyl group. And we want to know what product is formed. So what I have to do is I have to think, okay, well, this is a type 2 carbonyl. That type 2 carbonyl will accept a nucleophile. Typically, the double bond does not reform, and we have an OH that goes on where the double bond O is at right now. But in this case, it does not work that way because we are using a very strong base, a Miss America of the bunch, and that is a amine group. All right, so I've got to think primary amine. So what does a primary amine do? Well, instead of a double bond O, it is a double bond N. Remember that nitrogen comes in and says, oxygen, I'm the ringleader now. You've got to go. I'm not going to put up with you. You can't stay around. Bye-bye. See you later. So nitrogen is a bully, and that nitrogen makes the oxygen leave, and nitrogen takes its place. Well, with that also comes the alkyl group that nitrogen has attached to it. And that alkyl group is going to be a CH2 and a CH3R group. All right, so that is the product from that reaction, and this product is a amine, not an amine, but an amine instead. All right, so there's the product formation for that particular type of example. Okay, so that's an aldehyde reacting with a primary amine. So let's kind of do a ketone just to prove a point to say, guess what? Ketones can do the same kind of thing. So let's take this ketone group, and we have a CH2 and a CH3 on both sides, and we're going to react it with another primary amine. So this time I'm just going to flip it around on you, an NH2 over here, and then on this side we'll do a CH2 with maybe a benzene ring that is attached. And we want to know what product is going to be formed from this reaction. Okay, so no sweat. I'll use what I basically have talked about up to this point, and I'll go through and I'll predict the product just the same way that we've done all of the nitrogen-containing nucleophiles at this point. So I'll redraw the starting reagent. So here is a ethyl group to the left, and here is a ethyl group to the right. So I'm going to come in and that oxygen away, and nitrogen will come in to that spot. That's what the nucleophiles of the amines do, folks, with the top 2 carbonyls. All right, so that nitrogen goes on, and that nitrogen brings with it the R group, because once again, this is a primary amine, because that nitrogen is attached to only one carbon-containing group. So that nitrogen is going to bring a CH2 as well as a benzene ring to the party. All right, so I'll just kind of draw it up like this. You could have drawn it to the left, you could have drawn it to the right, you could have drawn it upside down. I don't really care how you draw it, as long as it's connected the proper way. So that again is an amine, not an amine. So that amine is the carbon double bond nitrogen to that R group. Okay, so those are 2 examples of a primary amine, one reacting with an aldehyde, one reacting with the ketone, in order to form the amine products that you see on the screen. All right, now let's go through and kind of do the secondary. And we know secondaries do not form amines, right? Okay, so here, let's take another ketone, and I'm just going to do a cyclopentane ring with a double bond O that points off of here to the right-hand side. It could have went anywhere. I don't care what it would have went. It would have been the same thing. And then plus, we have a NH, and then here let's do a CH2, CH3, and down here let's do a CH2 and a CH3. All right, so we want to know what would happen if this particular reaction goes forward. Okay, so what we have to understand is that it's still a type 2. We still have a ketone. And it's still a nitrogen-containing group. It's still an amine. The problem, though, is that this is a secondary amine because there's two alkyl groups attached to that nitrogen. So things are going to work out a little bit differently here. So this is the way that I like to kind of go through this product formation with these examples. So I'm going to redraw the starting reagent that we used, and there it is. This is a cyclopentanone. And that cyclopentanone is going to react with diethylamine. So this diethylamine reacts with the type 2 carbonyl, which is a ketone, in order to form a different functional group here. All right, so in the beginning, we can that oxygen away, and we can put a nitrogen there, and that nitrogen will bring the alkyl groups to the party with it. So a ethyl group here and a ethyl group there. So it brings all of the alkyl groups that is there. So here's our two R groups. The problem, though, is that right now, that nitrogen has 4 bonds. We cannot have it 4 bonds. It's not going to work. So this nitrogen forces that carbon to shove it inward. So this is an enamine. That is the functional group that gets formed. So this double bond goes away, and we form the double bond somewhere on the inside. Now, in this case, both examples are basically the same version. If I draw that double bond to the top, or if I draw the double bond to the bottom, it's really the same thing, folks. Now, the rules of alkenes still exist. So when you do this and you form that double bond wherever it might be, then you use the rules for an alkene that you learned in Chemistry 251. And basically what that said is that the more substituted that double bond's going to be, the more stable that double bond is going to be. So if you had a choice on which carbon that you wanted to create that double bond with, because they turn out to be different, then you're going to choose the one that gives it the most substituents. All right? More groups, more friends to the party. They watch after you when you get in trouble. All right? Okay, so let's take another example, and let's this time do just another ketone, right? We get the idea at this point. I'm going to do a 6-membered ketone here, though, so cyclohexanone. And we're going to react cyclohexanone with a 5-membered nitrogen ring. Oh, look at me now. All right, so that is still an amine. It still has an alkyl group. Right now, that nitrogen is connected to 2 carbons. So this is still, folks, a secondary amine because that nitrogen on the left is connected to a carbon and on the right is connected to a carbon. So 2 carbons are connected to the nitrogen, which makes that a secondary amine group. So this is no different. All right, so what we do is that I will redraw the starting reagent. There's the double bond to the oxygen, and I'm going to get rid of the O, and then in its place, I'm going to draw that nitrogen. So what did the nitrogen bring? Well, it brought the carbon that was to the left, and it brought the carbon that was to the right, and it just so happens that they are connected together in a ring. So I'm close to the product. I'm not yet finished, though. And the reason is because that nitrogen at this point has 4 bonds. We cannot have it 4 bonds, so it shoves it inward. And because it shoves it inward, this is an enamine. All right, so there is a double bond. It doesn't matter which carbon I chose to put the double bond between because they both are the same. So the double bond goes inward. That forms the enamine functional group, and that is the product from the reaction. All right. Okay, so let's take a look at maybe some more example problems. So here's an example. What's the product for the following reactions? Cyclopentanone with ethylamine, cyclopentanone with diethylamine, cyclopentanone with hexylamine, and then cyclopentanone with cyclohexylamine. All right, so this is where I'm going to stop the video. And I want you to go through and I want you to do some of these reactions, do some of these examples, see if you can actually predict the products here, because if you can do this, then you're well on your way to doing well on the upcoming test or exam. All right, so let's do these 4 examples in the next video when you hit the play button. So go ahead and try them, and then double check your answers, and then figure out where you went wrong, if you went wrong, but I've got faith in you. You are going to score a 100 on all 4 of these examples without a problem. However, if you can't draw cyclopentanone, then we have a bigger issue. So IUPAC will get you if you did not pay attention in the earlier video part of the series.